I mean, funny thing is everyone I asked told me the answer I gave you in the previous slide, which is the physical meaning, but without answering my curiosity about the word itself. The word comes from Latin, im plus pes pedis, or having feet in chains so that you cannot walk freely or run, hence the meaning of interdiction, limitation. In electrotechnics, it's the sum of the resistance, the real part, and reactances, imaginary, that altogether don't allow the current to flow freely. In mechanics, the real part is damping, and the imaginary part are mechanical reactances, all of which oppose velocity or motion. And then, as usual, there's the ans suffix that's used for complex quantities, more or less, usually. So back to equation. That's the equation of motion, the substitution I propose with the minus negative force. And the usual substitution, we obtain the equation of motion written in that way. But then I isolate the velocity instead of displacement, so j omega x outside the bracket. And that becomes zeta, which is force over velocity, or j omega x complex velocity, which is that one, that formula, that is the impedance. So mechanical reactances, that's the formula. So zeta is the impedance, c is damping, is the real part, and in the brackets multiplied by j, the imaginary unit, we have m omega, which is, I call it massive mechanical reactance, and k over omega, which is stiffness, over frequency, is elastic mechanical reactance. So what is reactance? It's the resistive or dissipative or damping behavior of components that are not meant to be dissipative, and occurs only in cyclic phenomena, not continuous ones. Not continuous ones. We can notice that three parts are present. Maybe the stiffness part is the structural damping or hysteretic, but what is the mass part? That above all can grow with frequency so much. And not the behavior of these three terms. Real part grows linearly if multiplied by frequency, stiffness 1 is frequency independent, and mass 1 goes quadratic with frequency. So to have myself an idea about the order of magnitude of these dampings, I prepared a table having considered both a greatly underdamped system and a greatly overdamped one. So damping coefficient, here is the table. Where you can see the dimension, the quantity of the system at the top. So mass is 1 kilogram, K stiffness is 100, so that again is natural frequency is 10 Hertz. I chose a damping of 0.15 that leads to a damping coefficient equals to 3, which is slightly damped as damping. And you can see the numbers that are incredible, because K omega and M omega, one at low frequency, one at high frequency, are immensely greater than the damping given by the damper, which is external to the system. But even if in the overdamped system, where I chose the 1.9 zeta, that gives a damping coefficient of 38, still the damping is lower than the one given by the two mechanical reactances. Maybe at this step near the natural frequency we have somehow an effect of the external damping. But as soon as we move through resonance frequency at 50 Hertz, M omega is already greater than the external damping. So somehow damping forces, the results were shocking to me. Nothing seems to beat internal or intrinsic to the system damping. I mean, now that we know that those are the numbers, we can clearly understand why a system not in resonance with the forcing one will oscillate poorly, of course. But what about the magnitude of damping force in respect of the driving one? Here is a point where I have doubts, because I think that each term of impedance has to be multiplied by j omega x, which means that we come back to the forces we see in the equation of motion when it's studied in Fourier way, that is to say elastic force, inertia, and real viscous damping. Hence, I'm thinking that somehow the situation might be the following, where in place of the damping coefficient, we have actually to compute the inverse Fourier transform of the impedance, which is a little more interesting. However, I'll discuss the modeling of damping coefficient in a future video. But the cornerstone is that for a free problem, not forced system, but free system, free oscillation, the system works in resonance, that is to say, at its natural frequency. Hence, mass and stiffness impedance parts, the two mechanical reactances, delete themselves respectively, because there's a negative sign between them, and viscous damping works quite fine. Outside resonance, instead, they become way more heavy and surpass the viscous one. And that could be the reason why damping viscous model works fine only for free oscillations and not for forced ones. But anyhow, going back to rectification, what I'm saying is that outside resonance, drive and internal damping balance themselves so that displacement is constant. Given the rectification example, the car. In resonance, driving force has no brake. Hence, the system is accelerated continuously, hence displacement grows to virtually infinite. The main difference, however, between resonance and outer zones is that in resonance, think again a rectification, the car on a highway, velocity increases at each time or cycle linearly. Hence, kinetic energy increases quadratically, then displacement and globally output energy grows too. And I'll give you here some numerical examples. Forces and energy, the system we used before, mass is 1 kilogram and K is 100 Newton meters. So the weight force is almost 10 Newton. Displacement at rest is force over stiffness, which is 0.1 meters, that is to say 10 centimeters, which is quite big, but this is a theoric experiment somehow. The energy, if we lift the weight exactly for the displacement at rest, is 10 Newton times 0.1 meters, which is exactly 1 joule. The elastic force is Kx, that is 10 Newton, and the energy, elastic energy, is 0.5, 1 over 2, Kx squared, which is given by the numbers, as you can see, and it comes out that the energy as the output is the energy as output is 0.5 joule, which is to say the output is half the input, which is to say more or less an efficiency, no? Which is to say an efficiency of 50%, which is already fine somehow. In resonance, where displacement is 20 to 30 times the one at rest, we choose now to take the displacement only 3 times greater. So we have the input situation remains equal. The output, as you can see, the displacement is 3 times before. So already the elastic force is 3 times the force in input force, the input force, but the energy incredibly becomes enormous, because the energy is 4.5 joule, and in input we have an energy equals to 1 joule. So output is already more than 4 times the input, and that's because the whole driving force is transferred to the system without damping or brake of any sort. Hence velocity rises, and so does energy quadratically. You might think on this situation. So forces balance, the same concept before, the same concept of the previous slide, but visually explained visually. Let's start from the rows of the elastic and inertia forces that are always balanced. So plus minus, plus minus, plus minus. Then look at the driving force row, which I gave a positive sign before resonance to convey the idea that before resonance, driving force and elastic one are synced, as I said in a previous video or slide. Is negative or opposite to elastic one outside resonance, beyond resonance, something like this. And at resonance, I gave a plus sign because driving force is always present, but is in quadrature with displacement. Is in quadrature with displacement, but is always present, and above all is synced with velocity. Is synced with velocity. So I put the plus sign, the positive sign. Then look at the damping row, and you can see that it's always negative, negative except for the resonance zone, which I gave 0. So then, if you compute the total for each column, you end up with 0. Plus or positive balance of energy and negative balance of energy. So if an external damping is added to the system at resonance, the force balance, hence energy, is positive, hence the displacement will grow virtually indefinitely. Velocity sync. You can also say that in resonance, force is synced with velocity, so maximum force at maximum velocity. And that is mathematically true, but to me it's the lack of the intrinsic damping the reason why displacement grows dramatically, quadratically actually, so velocity builds up linearly and energy parabolically. At resonance, as you can see, force and velocity are synced as the same expression. And once again, because there's no brake, velocity increases linearly and space quadratically as energy does velocity. So final recap. Given a cyclic force that excites systems at different natural frequencies, each one of them responds with vibrations, but only the one that has natural frequency equal to forcing frequency will show enormous vibrations. That is due, in my opinion, to the reciprocal cancellation of the two intrinsic to the system mechanical reactances, so that energy transfer is completely free. Acceleration is constant, velocity grows linearly at each cycle, and energy does so quadratically. If control of the system is required at resonance, an external to the system damping must be added. And that's the table we have seen before, where I colored the two boxes, the important boxes, to have a better comprehension of the energy balance. And we are done. Feel free to comment or contact me, and because we are on YouTube, please subscribe and click on the notification bell to receive updates on this and other ideas that I come up with. And consider to give a thumb up too, and share link or talk of this video with anyone that could be interested in this topic. So until next time, stay strong.